Hi, everyone. It's a real pleasure to be here. Thank you to the organizers. I've interacted with some of you virtually, and it's really nice to meet in person as well. I'm a research scientist at MIT. I wear two hats, really. One is as a nuclear scientist with the Nuclear Science and Engineering Department, and I'll give a technical talk later in the conference on applying quantum engineering to nuclear transitions. But I also wear another hat as a innovation researcher at the MIT Industrial Performance Center, and that's where we do a lot of what's sometimes called meta-science, so applying science to science itself, studying the social processes of science. And so in that sense, what we're doing here is a very kind of exciting process because we're in the middle of seeing a field information. And so we meet under this label, under this umbrella, quantum energy. And I think this is, I want to stimulate some discussion, some reflection in the course of the conference for us to think about and maybe interact as what it is that the scope and the knowledge base is of this potentially emerging field, what goals that field could have, where its funding comes from. So what are we all doing? How does it fit together? Does it fit together? And how do we want to relate to the outside world, like the public funders and so forth? And so the context really is that there's a lot of excitement, a lot of activity around like quantum 2.0, quantum research. So you see all these quantum initiatives around the world, but it's also remarkable that there's been this very strong convergence towards these three, sometimes four pillars. So you have computation, sometimes lumped together with simulation. You have communication and cryptography, and then you have sensing and metrology. And so you see quantum energy does not show up here. Where does energy come in? And so we've seen already in the talks so far that there are different notions of what quantum energy could be and where it comes into this. So one that's been brought up is these applications of quantum computing for energy technologies, for like more or less classical traditional energy technologies like improving battery chemistry of electrochemical systems, alongside other optimization applications of quantum computing. And then there are also what I would call direct energy applications of quantum engineering, which I'll talk about a bit more later. Like, it's also already been mentioned, accelerated exciton diffusion in organic solar cells, for instance, what James is doing in terms of new battery architectures based on work qubit instead of ion migration, and also what the kind of stuff that we are also working on, coherent control of nuclear excitation and de-excitation. So these would be direct energy applications. And then there's also another notion of quantum energy, which is the input into these quantum information science applications. And so there's actually papers that I think focus on different, sort of act as review or perspective papers on these different notions of quantum energy, these three different notions here. And so one perspective could be that as a field, there could be an emerging field that aims to be a kind of a fourth pillar here in these quantum initiatives and as they unfold in the future. And then there could be other pillars as well, like quantum biology and other quantum type of fields. But then there are also challenges associated with this when we now get into the social process of science. So there's a very active community in the US around meta-science and the social processes of science. And so there is this argument by Michael Nielsen, who's also done some pioneering work in quantum computing, that science today, the social process of science, are bottlenecked around the formation of new fields. So that's something that, as a community, we'll have to contend with. And in the US in particular, as a response to this recognition, there has been kind of the emergence of new alternative research organizations and research funding mechanisms. So here are just a few examples. There's these focused research organizations that have also been described as nonprofit science startups. There is the ARC Institute. A lot of these are philanthropy-based. Actually, Convergent Research is a Boston-based kind of an incubator that has raised $100 million in philanthropic funding that sort of spins out these nonprofit science startups. So that's something maybe for us to keep in mind as a forming new field. And so, but probably it's best to aim for engaging with both those types of, to be aware of those types of new and alternative funding mechanisms, but also the traditional ones. Okay, so, and I guess that what I'm already implying is that we can't rely on the optimal outcomes to fall into place by themselves. So again, science is a social process, and often what is pursued in science is, it's also what the argument by Nielsen and his co-author, what is pursued is what's fashionable, politically popular, or media friendly. And so sometimes if we don't play our cards right, certain things get left behind. So we need to be strategic, need to communicate well, need to be proactive. And so I think that requires answering this question. So if we want to be a field of quantum energy, what's our profile, what's our identity, who are we? There needs to be some sort of coherence in a field and some setting of scope. And then what are the goals? And goals also articulated in a way that the public and that funders can understand, because ultimately that's what determines where the support comes from. And so, that this is sort of looking at from another perspective again, the perspective I've had, and again, all of this is subject to debate and to discourse. And so I'm curious for people to come up and present their perspectives. But so one could see quantum, for instance, quantum battery engineering as being like a niche or margin of battery engineering, or I could see quantum-based solar engineering as a part of solar engineering, but then these would all be niches or fringe areas of these established fields. But one could also say there is a field of quantum energy that sort of overlaps with some of these more traditional engineering fields. And so that's also just to stimulate maybe this kind of perspective. So what defines the scope and identity of a field? Here, I think the reference would be Thomas Kuhn, who described this field as comprising a set of shared theoretical beliefs, common models, and examples, values, and instruments and techniques of a scientific community. In practice, that's what's being taught, basically, in an educational program, what's in a textbook eventually. And so, together with some co-authors, I've written this perspective article. This is the main figure from it, where we kind of compared quantum computing systems with approaches use quantum engineering in solar applications inspired by photosynthesis, insights, quantum batteries, and also quantum nuclear, what sometimes called quantum nuclear dynamics. And so in the appendix, so the perspective article is quite short, but in the appendix we also look into the kind of Hamiltonians, the way these systems are modeled by the different authors, and they're remarkably similar. It's always the kind of, and so that's again from my perspective, these are Dickey models and variants thereof. Often Dickey enhancement plays a role in the form of superradiance, superabsorption, supertransfer. There's loss, noise, enhanced transport, down conversion, up conversion, but there could be more, and I'd be excited to engage with you and understand what could be sort of what could be key concepts of a field of quantum energy. And then in our case, we use QTIP a lot as a sort of a tool, and I think so we're building up our own code base, and we're benefiting from other. So QTIP, I should say, is a Python library for modeling quantum systems. And so if we then think about this as a basis, as the kind of maybe profile of scope, here we can think about potential impact and goals that could also be communicated to the public and to funders. And so there's the technology readiness levels from 1 to 9, indicating different degrees of maturity of a technology. And so our perspective is that it's actually a nice mix, these different groups of quantum solar, quantum batteries, quantum nuclear, in the sense that quantum solar is fairly far along, in the sense in the last 2 years there have been a number of papers that describe like using delocalized states to accelerate exciton diffusion, and then also fabricating nanostructures that have this accelerated exciton diffusion. So that's been demonstrated. As for quantum batteries, there was James's paper with a quantum battery prototype, and quantum nuclear is the area, again, I'll talk about it on Wednesday, that's kind of still really deep in basic research, but also with potentially very large impact. Okay, so this is then the question in a field, what would be a scope that's not too narrow and not too broad? And so probably a good scope for a field is to have some sort of portfolio that has some visionary aspects to it, but also some very substantiated aspects. And so, for instance, this raises a question, something like quantum superchemistry using Dicke enhancement to accelerate chemical reactions. Should that be part of quantum energy, or is that a separate pillar altogether? So these are the kind of questions that come up when you think about scope and goals. And then there's things like, if there is more of a sense of a field, there could be, there's these conferences, there may be journals in the future, workforce training programs, and these things may be different from region to region depending on what the strengths are. But I think it could be, interesting to start by submitting people writing white papers, maybe people working with their local funding agencies, and submit things and then share the responses and share these ideas in this community and learn from each other. And funders often also respond to each other. If there's a big funding program in the US, then people in Europe will pay attention and so forth. And then finally, I'd like to just mention I think we have a big opportunity here to make an argument that's not made very often, namely to shift away from, to provide a means to shift from one S curve to another. S curves are these performance curve, how a technology improves in terms of its key performance metrics. And you can see on the right the S curve for power density of electrochemical batteries. And you see there's a saturation towards what's the theoretical limit for the electrochemical battery. But then if you have a different physical principle underlying this technology, then you have a different S curve, and you can have discontinuous jumps in performance. And that's what you basically get when you move from an electrochemical battery to a quantum battery. And so already in James's prototype, you see a higher power density than would have been considered theoretically possible for electrochemical battery. So I think these are the kind of arguments we need to make for this field, for this approach. And so maybe we can even think bolder than just being an extra pillar in that sense. Maybe we can view ourselves as a counterpart to quantum information science. So that would be quantum energy science. And that the definition would then be quantum energy science is the use of quantum principles to transfer, store, and convert energy. Quantum principles being the quantum 2.0 principles, and as a counterpart to quantum information science. And of course, information and energy are two sides of the same coin. Take the capacitor, which can be used for storing information through energy, or for you can also use a supercapacitor where you don't care about the fidelity of the information, but you care about the maximizing energy. And so the same with qubits and work qubits. So I think we have a huge opportunity here. There is this big hype about quantum. There's this big attention on energy, on decarbonization. And I think if we do it right, then we can tap into this excitement. I think there is a chance to really be at the center of this rather than being kind of at the fringes of existing fields. I think that's the opportunity that we have ahead of us. Thank you.
Thank you for that very nice questions.
This may be jumping the gun on your subsequent talk about quantum nuclear, but outside of the thorium clock transition that people are looking for in the precision measurement community, I'm wondering what are the other coherent processes that would be potentially accessible in a nuclear system with conceivable technology?
Yeah, I think a key paper is a 2018 Nature Physics paper, Chumakov et al., where they showed superradiance, experimental demonstration of superradiance of the iron 57 14 kV transition. So an acceleration in their paper, I think, of a factor of 15 of the nuclear de-excitation. And what we are interested in our work at MIT is to not only work with superradiance, but apply the supertransfer to see supertransfer in nuclear systems. And if that's achievable, you can conceive of moving nuclear energy around between different systems, and that opens up a whole new world of nuclear engineering, quantum coherent nuclear engineering, if you like.
Thank you very much for the meta talk. That's really interesting. Did you manage to put quantum energy in the strategic program of the US for quantum, or did you try?
No, we haven't. I mean, we only started engaging with stakeholders about quantum energy maybe earlier this year. So yeah, I think we would very much like to work with everyone to think and strategize about where this concept should be positioned and how and at what timescale.